Now we're continuing our discussion of these bonding formulas for differentiation. I call them bonding formulas. I think of the small pieces as sort of like atoms in a molecule that are bonded together, but there's various kinds of bonds. The constant multiple is not really a bond, but we talked about that last time. You could add them together. That's one way of doing it. You could subtract them, and those are all the nice ones. This video we're going to take a look at the product rule and then the quotient rule, chain rules for part 3. So what people often like to do, because the sum rule is so nice, that derivative of the first plus the derivative of the second, derivative of the first minus derivative of the second, they assume that the pattern continues. Even though the pattern didn't work here, it wasn't derivative of 3 times the derivative of x to the 5th, that would just be 0. But people want to make the product rule the same thing, where you look at the derivative of the first times the derivative of the second. So before we go into what it actually is, let's see why that can't work. Say we had x to the 5th times x to the 1/3. We're looking at the derivative of those. And that's the cube root of x thing. Is that the same as the derivative of x to the 5th times the derivative of x to the 3rd? Well, this left-hand side is 5x to the 4th times 1/3 x to the negative 2/3. Let's do our multiplications. That's going to be 5/3 x to the whatever 4 minus 2/3 is. So that's 5/3 x to the 12/3 minus 2/3, 10/3. Well, that's the left-hand side. Sorry, the right-hand side. This here, we could have gone about this a different way. We could have just taken the x to the 5th times x to the 3rd, and now we're taking a look at x to the 15/3 plus 1/3, so that's 16/3. Okay, well then that's going to be 16/3 x to the 16/3 minus 1. 16/3 minus 1 by power rule, so that's 16/3, 13/3. Well, as long as you think that this is equal to this, you're fine, but I don't think anyone should think that. Perhaps the easier example with friendlier numbers is if we're looking at x squared. You know from power rule that ought to be 2x, but that is very different than what the derivative of x times x is. Well, no, that is the same as what x times x is, but that is different from the derivative of x times the derivative of x, which is 1 times 1. So those don't work either. So it can't be do each piece individually, differentiate each factor individually. It's got to be something a little bit more complicated than that. And the question is, what should it be? Well, one way to sort of get some intuition here, I'm not going to work through the limit. It's a big mess of algebra that ends up showing that it's true without really showing you why it ought to be true. It just shows you that it has to be true. So I'm going to start with the formula, which I don't always like to do, but here's the starting with the formula. The derivative of f times g ought to be the derivative of one times the other plus the other way around. Everyone gets a derivative one at a time. F gets a derivative turned to be the derivative times g of x comes along, plus f gets doesn't get derivative, but the g does. And it doesn't matter, because the beauty of commutativity, it doesn't matter what order you write these in, just as long as it's a one derivative but not the other, and then other way around. There is a 3-term version of this, which, while it doesn't really show up very often, because you don't often have 3 things multiplied together, at least in a classroom setting, it gives you some intuition as far as the pattern that this is a part of. Because after all, it's f prime g h plus f g prime h and f g h prime. Again, everyone gets a turn at being the derivative, then everyone else just comes along. And it makes sense, because you're only taking one derivative here, so they should only get one derivative at a time here. They shouldn't all be happening at once. That'd be too many derivatives at once. So why should this be true? Why should that be the mess that it is? Not just y can't be the other thing, and not because the algebra says so, but why should it? This is a demonstration of why it ought to be true, not a formal, rigorous proof. So say we have a rectangle that is growing over time. The time is going to be x here. We'll say the width is f of x, and maybe it's growing like x squared as we go. Well, let's call it x squared, sure. And its height is a g of x, which we'll call square root of x, just to give some concreteness to this. Well, over time, this is growing. And I want to highlight that I've picked functions that always give you positive answers. If things start getting negative, things start getting weird, but it still works there. So this is growing over time, where it's sort of growing at different rates. The width is getting much faster, bigger, faster than the height, but whatever. And so we add little bits to it. So as time goes on, it's getting a little wider. It's getting a little taller. I'm going to color code this, and that's sort of the intersection of those two additions. Well, by how much? Say we go forward h time units, h seconds, let's say. Well, then the new width is going to be f of x plus h. Whatever x was, you add h seconds to it, usually a fractional second, so that's x plus h squared, for example. And then here, we add h seconds, and so the new height, there, is going to be g of x plus h. I'll write that sideways, and so that'll be square root of x plus h. So that's the new thing, which means the bit we've added is really based on the derivative. This little bit that we've added is f of x plus h minus f of x. How quickly are we adding it? We're adding that much area per h seconds. So that's going to approach, I won't say about equals, I'll just approach as h gets small, it's going to get toward f prime. It's going to be that width. And likewise up here, that height that gets added is going to be approaching g prime of x, for the same reason, except for g's instead of f's, and I guess it's in red. So what area are we adding here? We're adding some red area, and we're adding some blue area. And we're also adding some green area. And so the amount that we're adding, the area, well, normally is f of x times g of x. And h seconds later, we're looking at f of x plus h times g of x plus h. But really, that is this black area in here, which was that original f times g of x. I'll put it about equals for the moment, that inside area, plus the blue area, which is approximately f prime of x times that horizontal, times that height, which I'm stopping there, which was the original g of x. G of x plus the red area, and so now that height is the g prime of x times the width of the red region, which is that width, so it's f of x, plus this little extra green bit, which is problematic to say the least. It is going to be, let's see here, about f prime of x times g prime of x. But now this is where I cheat a little bit, and this is the cheating that Leibniz had to do too, so I don't feel so bad. I'm in good company. This bit goes to 0 as h goes to 0 much faster than the rest of this stuff does. And so when it comes time to do a prime of x, which is that a of x plus h minus a of x all divided by h, Well, when I compare a of x to a of x plus h to a of x, I get these two terms that would subtract to 0. And all I'm left with is the f prime times g of g and the f times g of x. And so in the end, that's the part that matters. This can all be done rigorously with h going to 0, but it's not really worth doing it now. It comes down to the way that areas get added, though, is the long and short of it. That's why it ought to be as weird as it is. So let's take a look at an example of this. So what should it be? The derivative of x to the 5th times x to the 1/3 ought to be the derivative of the first times the second plus the first times the derivative of the second. And now it's a matter of cleanup. So derivative of the first times the second copied over, first times the derivative of the second. All right, let's clean this up. X to the 4 plus 1/3 is 13/3 plus, that's 1/3. 5 minus 2/3 is also 13/3. That's 5 plus 1/3 x to the 13/3. 15/3 plus 1/3, that's 16/3. And if you go back to the beginning of the video, that matches up exactly when we just wrote that as x to the 16/3 and bring that down in front and subtract 1 from the power. So yeah, this seems to be working the way it ought to. Let's take a quick look at the quotient rule. So the quotient rule is a bit more complicated, just because division is always worse than multiplication, isn't it? But say I've got f of x divided by g of x. And here I don't have a rectangle to draw. It comes down to this is how the algebra works out, which is, I know, unsatisfying, but this is how the algebra works out. And the way this has various forms. One of the ways to do it is as follows. Nope, it's not that. Go erase your notes. Let's start over there. This is why I do these in one take. So let's take a look at the derivative of f of x over g of x. Now, it is the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Again, one derivative at a time, just like product rule, except now because of the subtraction, you got to be careful about which comes first. Otherwise, you're going to get it backwards. I just want to highlight how the denominator does not have a derivative in it at all. I mentioned there's various forms. There's other forms such as break up the subtraction and you get f prime of x over a single g of x minus f of x times g prime of x over g of x squared. That's also legitimate. This tends to be the form that people like. This is going to be useful when we go looking for things like when is the derivative 0? Because in that case you can focus on just when is the numerator 0. Whereas here that's a bit more annoying to figure out when this expression is 0. So I mentioned how the order matters. There is one way of doing it where you think of this as the derivative of low and high, or just L and H, which I'm going to use, where there is low d high minus high d low all over low. Sometimes you're low or low squared, whatever. It's the top that's the hard part to remember. And it has a bit of a rhythm to it, low d high minus high d low. And you say it enough times, it just sort of sticks in the brain. I won't say it the other way around, so you never have to hear it. It also helped that when I actually took calculus as a high school student, there was actually a girl in my class named Heidi Low. And we had to be, the teacher made her leave the room every time we did quotient rule so that we would be minus Heidi Low. And that way we would all remember the way that it should be Heidi Low with the minus sign. Poor girl never learned calculus, but the rest of us did. And so this is the quotient rule. Let's take a look at how this works out in practice. And then I'll end the video. So this is x to the 5th over cube root of x. That was the one I was interested in at the beginning of the video, at the beginning of the last video. Low, derivative of the bottom, or low times the derivative of the top, 5x to the 4th, minus high d low, derivative of the bottom, 1/3 x to the negative 2/3, all over that bottom squared. And now it's just time for cleanup. This is 5x to the 1/3 plus 4, so that's 13 thirds, minus 1/3. This looks a lot like the product rule, and it usually will. X to the 13 thirds, oh good, those will combine, all divided by x to the 1/3 squared, so that's 2/3. And let's simplify a little bit more. 5 minus 1/3 is 14 thirds. 15 thirds minus 1/3, 14 thirds. X to the 13 thirds. And I'll, rather than divide, I'll multiply by something with a negative exponent. And that lands at 14 thirds, x to the 11 thirds. Which I want to highlight is what you would do if you just did power rule from the beginning. For something like this, I really recommend what I call prepping the patient. Make it simpler before you go trying to divide, because sometimes you can save yourself a lot of work. So this is x to the 5th over x to the 1/3, so that's x to the 14 thirds. And now we do power rule, and we would land there too, with far less work. And thank you. That is product rule and quotient rule.